Yeah, so we've heard on this stage already a couple of times today, build, baby, build. So it's an important moment to think about what are the materials we're going to use to build, baby, build. When we think about the future, we often talk of energy, but energy and materials are inextricably tied together. Right? It takes lots of materials to produce energy, and it takes tremendous amounts of energy to produce materials. Today's materials, like steel, aluminum, and copper, consume more than 12% of global energy production, responsible for more than 8% of global CO2 emissions. Now, you've probably heard about the Herculean efforts we're going to decarbonize these materials, but I'd like to do a little experiment. By a show of hands, who believes that we will successfully decarbonize steel, aluminum, and copper by 2030? No one? All right, okay, let's make it a little bit easier. How about by 2040? Show of hands. Okay, a little more optimism. How about 2050? Okay, all right. But a divided room. I see some skeptics out there as well. Well, the truth is, we will not successfully decarbonize these materials by 2050, but maybe not for the reasons you think. We will not successfully decarbonize steel, aluminum, and copper by 2050 because by 2050, steel, aluminum, and copper will be obsolete. So it's a bit of a trick question. These are actually not today's materials, they're yesterday's. So I'm Bryan Guido Hassin, I'm the CEO of DEXMAT, where we produce an advanced nanomaterial made of pure carbon called Galvorn. Galvorn is many times stronger than steel. It is much lighter than aluminum, lighter than carbon fiber even, and it's as conductive as copper, but it's produced, not like most materials, by combusting carbon. It's actually produced by capturing carbon. So I brought a small sample. We actually make it in many different forms. This is our industrial fiber, and this is actually about 13,000 meters of our industrial fiber. Depending on the grade of steel you're comparing it with, this is 10 to 20 times as strong as steel. And just as a thought exercise, I would challenge anyone in this room to try to pick up 13,000 meters of steel cable or copper wire, not to mention, be able to toss it around. And part of what's neat as well, when Galvorn reaches end of life, we can scalably and efficiently reform it into new Galvorn materials with no loss of properties over and over again. So it's a truly circular material. Now, often one of the questions we get is, okay, great, incredible properties, sounds like a magical material, but what can you do with it? Right, and the mundane answer is, well, what can you do with steel or aluminum or copper? Because generally Galvorn can do the same things, in many cases better, because of the better properties. So for example, we can build bridges that are 20 times longer than bridges that are constrained by the weight of steel. But what interests us more, and especially in the spirit of kind of magical technologies, is what are the new things we can do with materials like Galvorn that we cannot do with yesterday's materials? Things like advanced power conductors and power transmission lines that are stronger, lighter, more conductive, and more resilient to extreme weather. Next generation data centers that are much more efficient with how they process and transfer heat and use much less energy. Lightweight, flexible garments that protect you from cuts, from ballistics, while simultaneously keeping you warm or cool, and simultaneously collecting your vitals and transmitting them as well. So the application space is massive for materials like this. The historical challenge has been cost, but that's because we're producing it at a really small scale for these kind of magical applications in space. And it turns out that Galvorn production enjoys incredibly steep exponential learning rates, steeper than solar, steeper than batteries even. And so just to put that in context, when Galvorn was still being invented in the lab at Rice University, so it was invented by Nobel-winning scientists there, the cost to produce it was on par with mythical materials like unobtainium. Since spinning out from Rice a few years ago, DEXMAT has scaled up production by 3,000 times and reduced cost 99.6%. And so it's expensive, but it's now at cost parity with exotic materials like gold molybdenum and bismuth telluride. But that enables Galvorn to displace those exotic materials in exotic applications like thermoelectric generators, which obviates the need for batteries in devices that are out in the field, and a bunch of other pretty exotic materials for which we were featured just last month on the cover of Science. But as we scale up a further 3,000x, which should be just over the next couple of years, we'll hit cost parity with specialty materials like carbon fiber and Kevlar. And as we scale up a further 3,000x, then we'll hit cost parity and actually even below cost of commodity materials like steel, aluminum, and copper. And historically, that's the right combination. When you have better properties at lower cost, that's when incumbent materials become obsolete and there's a massive materials revolution. So while we ask, how are we going to power the future, we must simultaneously ask, with which materials are we going to build that future? And it won't be with yesterday's materials. It'll be with materials that today seem like magic, but tomorrow will be as mundane and ubiquitous as, as carbon.
Amazing. Thank you, Bryan. Okay, we're going to ungainly swap you over with Rodolfo. So yeah, why don't you pop up and I'll get you back up. So thank you. I love Galvorn. Super magical. I forgot to ask, you're carrying this around so people can
for sure.
come and find you and you can touch the future. So next up, tackling this enormous requirement for how we build computing that uses much, much less energy, Rodolfo Rosini. Thank you.
Hey everyone, my name is Rodolfo. I am the CEO and co-founder of Vaire Computing. We're based in London and on the West Coast. So you heard about unobtainium, and now you're going to hear about computronium, right? So the goal of our company is to build the most powerful computers possible, and I'll explain what it means at the end of this. So it's going to be a short talk, but basically, John von Neumann made the most important discovery of the 20th century in the 1950s. He didn't write it down, and then he died, right? So luckily, before dying, he talked to someone, to a young physicist. So what he figured out was why computers get hot. He started looking at the earliest computers, and there would be no reason for a computer to get hot, right? So a car takes fuel, transforms into kinetic energy and it's in motion, and a light bulb takes electricity, turns into light, and so forth, right? But why computers get hot, right? Computers are supposed to take electricity in and spit information out, right? Not heat. And he sort of figured out that the main reason why computers get hot, right? And it's not the only reason, right? In this talk, I'm going to brush a lot of details under the carpet. The main reason is because we erase information, right? On a chip, we destroy information, we merge a branch, we change the state of a gate, and this results, right? Energy in, a bit of computation, and heat out. All these erased bits on your computer becomes a puff of heat on the other side. And this is, at this point, it's almost 100% of the energy in a computer. So your computer is a heater that happens to perform some computation as a very, very, very distant second. And so the way he saw it was basically this. They weren't chips at the time, but like for some poetic license here. The idea was that you take something that is energy, raw energy, and you turn it into information, right? And you can put as much energy as you want into the system, but if you're inefficient at converting it, right, that doesn't work. So this poor physicist that got this brain dump from von Neumann basically spent 10 years trying to figure out what this guy was talking about. And finally, in 1961, he invented something called reversible computing. And if you have never heard about it, this is your time to take a photo and then Google it and go into a rabbit hole. If you have heard of it, you're going to be like, oh my God, this doesn't work. It's not true. So reversible computing is the concept that, yes, you erase information, and so you release heat. But what if you didn't erase information? What if you had a chip that actually would retain all this information and reuse this information internally? This would basically give you the most energy-efficient chip possible, right? There are a number of architectures out there, right? Analog, neuromorphic, classical, digital, so forth, right? And if you look at sort of the spectrum of energy efficiency, if you reach like the very, very end, this is what you find. There cannot be derived from the second law of thermodynamics anything more efficient than this. Carnot said so, and Richard Feynman said it as well. So, who am I to argue? And the way that you build these chips is essentially, again, this is like an hour, this slide, but in practice is you have information that can go forward and backward in a gate. What this means, you don't destroy information, you retain it. And then you have a device that is quite like a pendulum that essentially captures the energy and then sends it back, right? It has the drawback that you have to redesign the entire chip, but it's something that we did. And so we've created the first near zero energy chip that by near zero, we don't mean just it uses near zero energy. It's more, it dissipates near zero energy. And this matters because if you know anything about computer building, like yes, you can save on these transistors, but then of course you have memory, you have interconnect, so like all these other components that leak information and take energy, and so it's not just like, I'm not trying to sell you snake oil on this one. But the reason that it matters is because if you have near zero energy dissipation, then you can do things that other chips cannot do, right? So chips, for example, have a single layer. Chips cannot be too close to memory, and this sort of like you can do it. It's called magical, but this is not like in the far future, right? We designed this chip, and we're going to have it in April. So, yeah. Hopefully, you see some front pages in April. We were on the front page of the IEEE magazine. Well, we are this week with this, so hopefully you hear more. And this is most outrageous. So we think that we reached basically the end of what it. So the classical Moore's law ended in 2005. Now, and we are in the world of multi-core processors, and that's also reaching the end, right? The next iteration will have to be reversible. There will be multiple implementations. We're just one of them. But you'll see this is the first, and it will be basically, this is how we're going to be building computers probably for the next 100 years. Thank you.
Stay on, Rodolfo. Bryan, why don't you come and join me? Come, take a seat.
Thank you.
Wow, okay. Let me just hold the ring of Galvorn. I know, 13 kilometers. Bryan, you heard Rodolfo present from the sides there. What do you think? You think he's got a bit more magic than you?
Well, first, I think it's not a competition. I think magic is a renewable resource. I will say I'm very impressed by what Rodolfo's doing, and it's one of the reasons I tell my team not to invest too much time in our data center applications, because maybe moving heat more efficiently may not be, there may not be much of a future in it. But it's interesting. We're in very different fields, but I think the problem space is quite similar, right? It's easy for the vast majority of solution seekers to be constrained by what are effectively artificial constraints, right? So in the case here of, oh, well, we assume that chips will have to create heat, and we just have to find ways to process all that heat, liquid cooling, whatever we have to do. In our case, we assume that materials have to come from processing tons of rocks into kilograms of usable materials in a thermodynamically kind of incomprehensible way.
Yeah.
So you just have to, you throw away the constraints, and suddenly the solution space looks a lot more interesting.
When you look at either of these products, they do feel sometimes a bit incomprehensible. So, Rodolfo, you started this. You started Vaire. You started on this journey a few years ago. What was the moment, the lesson you can give to people in the room about the plausibility of this type of magic?
I'm trying to be diplomatic, but basically...
It's late, you can say what you like.
So I'm not going to name names, right? About 10 years ago, I was doing AI, and I met this guy who also wanted to start an AI company. My God, that guy was incompetent, right? And, but he never gave up. And he recently won a Nobel Prize. And I was like, okay, maybe, being competent is not necessarily, right? It it is agency, really, and resource coordination and not giving up. And really, like, you can move, like, you don't need a lever big enough. You'll find the lever, right? Like, and really, like, I hate this guy because, like, gave me this great lesson, but yeah, so.
You just have to get going and see.
Just, like, it doesn't matter, right? Like, if you don't do it, no one else will. There is no perfect market. There is no nothing, right? And really, like, 7 billion people, right? There are like 3 people that did AGI, right? To really start. And now there are a bit more, right? And so that's I would say, the great lesson.
So there are similarities between both of the products here and projects here, which is they are really quite hard for people to get their head around. When you say this is a near zero chip, when you say computation is about the destruction of information, when you go and say, well, it's stronger than steel, more conductive than copper, lighter than aluminium, and it's carbon negative, my response is no comprende. So how do you go about, what did you find when you were explaining to people what this was? How do you go about bringing them onto your page?
I mean, in our journey, and to be clear, we're still pretty early in our journey. There's probably a lot more to learn along the way. We find there's a lot of value in seeing as believing, or touching as believing. If I showed you a PowerPoint slide with a material that's in 2 dimensions, and trust me, it's really good, that's not all that helpful. Like, if it's something you can touch and feel, that's a lot more helpful. In the case of customers, investors, et cetera, I show you, qualified testing that's happened on it that demonstrates the properties, including, as I say now, which has been published in some of the most preeminent scientific journals in the world, that starts to bring people along. But it still requires more than that, but it's a good first step.
Yeah. Rodolfo, how about you? What was the response? I mean, think about what you've learned from how you would explain what Vaire does to people for whom it's outlandish.
Yeah, and so I'd say the weird thing for us is that, so I just want to make something clear, like, we didn't really invent this technology. This technology was built by MIT in the 90s. And nobody built a product on this. There was literally, like, anyone could have done it, right? So the issues for us was figuring out that right now, that type of compute, because everything is trade-offs, right? And figure out that the trade-offs, it used to be the trade-offs in the 90s, were no longer that, but actually were positive. So it was more about figuring out how do you create a cycle, a financial cycle of, you put money in, as you were talking with the Commonwealth system guy, right? Like, you put money in, you buy it, you build a product, and you can show this sort of dynamo, right, kicking in. Once you figure that cycle out, everything becomes downhill, right? Because you can find the people and everything. So that was the hard part, I would say.
There's something that you said, I hadn't realized in the time we've talked about this, of course, that the technology was there, but it had been, in a sense, orphaned because there was so much velocity and scale in the traditional computing industry. It was yielding returns. I wonder how many amazing magical technologies are sitting in university labs around the world. I mean, Bryan, you did quite a survey of this, I think, when you were thinking through your journey to DEXMAT. What was your experience?
So yeah, I was looked at thousands of technologies that could have the kind of impact that I was seeking. And by the way, I now sit on a board of an NGO that specifically tries to accelerate the tech transfer out of universities and national labs, because there are tens of thousands of those technologies sitting on the shelf. And some of them may be pie in the sky and never have applicability. Some of them, though, may be right place, wrong time, and just waiting for the right. And that was the same with our entire field as well. You saw the exponential cost down curve. A few years ago, I couldn't have told you, oh, this legitimately could displace metals at scale, whereas now we can. So there's a time dimension, I think, as well.
Yeah, and do you see that time dimension as well, Rodolfo? I mean, your journey is slightly, it feels different with a chip, right?
Yeah, so again, in the 90s, right, when this technology came out, people looked at this technology, they looked at Intel, and it was like, okay, I'll buy Intel, right? And so things sort of like Intel's architecture reached a point, right, and where it struggles to grow, right? And by the way, we got a lot of help from Intel on this, right? So it's not that they're completely oblivious to what's happening. But yeah, it's mostly you you'll love this, right? It's every exponential is an S curve, right? And so basically your job as an entrepreneur is figuring out, are you, which part of the S are you, right?
You want to get to that bit of the S, not that bit of the S.
Yeah, and or figuring out what plateaued, and so you figure out what other scaling, right? And so this is why, like, I'm not selling you this because, like, quantum computing, right? People sell quantum computer. Oh, I spent 30 years doing quantum computers. Like, I mean, I don't give a shit about my technology in the sense that I could be selling you something else. I'm selling you this because this is the best one, right? Not because if it wasn't this one, I would do something else, right?
Right. Yeah, but a pragmatic magician. We've got a couple of minutes left, and what I want to do, like, as we bring the sessions to an end, is throw out the the crystal ball, the sense of the difference that these things could make to the world if we believed them, if we started to buy them, so prices could come down and we could use them really, really extensively. Just in a brief, paint a bit of that picture with the world of Galvorn.
So it always happens with materials revolutions, right? There's the actual innovation itself and then all of the ancillary innovations on top of it. It happened with steel, which then unlocked rail transportation, unlocked skyscrapers as well. So it's hard for us to imagine the ones that we see very immediately. So we have a number of customers in the aerospace, so lightweighting planes, but also electrothermally.
That sounds boring. What about space elevators?
I hesitate to use space elevators because they've been, just around the corner for the last 30 years. But for the first time, they're materially, no pun intended, possible. But again, there are multiple steps, right? You lightweight airplanes, and suddenly electrified aviation is possible. You put this stuff in roads, and suddenly electric vehicles, already lightweighted by the material, can be charged while they're driving, and battery range becomes no longer an issue. So it can fundamentally shift the ways that other technologies roll out.
Reinvent the auto industry. You said that in Germany. That's a good pitch to make here. Rodolfo, your crystal ball, what's Vaire going to do for us in a few years, in 10 years?
Right. So one computer in the world requires a power station, 1980s PC, power supply unit, right? You plug into the wall. Phone requires battery, right? The next iteration is 50, and everyone has one, right? And now you have like probably 4 or 5 computers around you, right? So the next iteration is 50 computers in your brain and all around you talking to each other that don't use batteries. They just harvest energy from the environment, and they're everywhere, right? And sort of like in an explosion of machine intelligence that we cannot even imagine, right? So that's and this is the curve, right? Like, so.
An amazing picture both of you have painted. Thank you so much for bringing the magic.